right, the warm-up is a Dijkstra's. So hopefully you had some practice in section. This is a great group problem to work on. So go ahead and take the next 5 minutes and try and trace this Dijkstra's all the way through. Okay? Means fill out this entire table. How are we doing time-wise? How many people at least have processed to vertex E so far? How many have gotten as far as E? Oh, that's like the second one. Okay, cool. Then let's talk about it. I don't want to just waste your time. Okay, cool. Let's talk about it. So remember with Dijkstra's, the way that we move through the graph is we start from a source vertex. You've got to have a source vertex for Dijkstra's. And then we set everything else's distance to be infinity. Now we start from our source and we look at our outgoing edges. And we have two options for our outgoing edges, which means that we will mark A as visited And now we've got a sort of estimated distance for both C and D. Which one are we going to pick? Where do we go? C or D? Anyone? Yeah. Yes, we go with D, absolutely, because D is a distance of 1, and we're greedy. So we're going to go to the one that works best for us in this moment. So we're going to go to vertex D first. Now we're going to mark that one as known, and now that is guaranteed to be the shortest distance to vertex D. But I didn't mark C is known, because I looked ahead and it has a distance of 2, but at that moment in time, that wasn't the shortest possible move I could make. So I'm going to wait to mark that as visited. So now that I've gotten to D, I have a few more options because D has a lot of outgoing edges. So the red there, those are my new possible places that I could travel to. So now I need to make the decision again, which vertex am I going to go to? Anyone? Anything that's not marked visited? Yeah. E. And why did we pick E? E is correct, by the way. Yeah, please. Yeah. So E, when we're looking at this selection of choices, we can either go to B, C, E, F, or G at this point, because those are all sort of they have some known path. It's not infinity far away. Infinity, i.e., I have no idea how to get there. And so those are the things that are in our options. Anything that has a known path and isn't yet visited. And then we just pick the smallest one, E. Or C. Oh, you look at, I have 2 actually. You could say C or E because they're equivalent distance. So I'm okay with you doing either. That makes sense. Same properties though. Does anybody have any questions on how we're making those decisions? Yes, please. So thank you for asking. The question about is how do we actually get there? It's all based on this edge 2. So right now, choosing C being just another one of the lowest possible distances I could travel, I didn't travel from D to C. I'm technically traveling from A to C because A was the outgoing edge that gave me the distance 2. So when I marked it as having a distance 2, I marked, well, where am I coming from in order to accomplish that? So if I go backwards, I originally put this A here for C and D, representing these 2 outgoing edges. And then as I sort of meet new things, that A sticks around. So I'm not actually just walking a singular path. I'm sort of exploring the graph based on the outgoing edges and then always coming back to evaluate in the things that I have possibly encountered so far, what's the next greediest, what's the next shortest jump I could possibly make. In this one, it happened to be from A along that C edge. But like I said, you could equally have chosen E because those things are the same. And that would have been a travel from A to D to E because that's how that edge 2 is shaking out there. Yes? It's the shortest that we've seen so far. Yes. If you want to think of that as shortest from the start, it's not a direct path that we're walking. It's about as we're exploring the graph, what has become available to us? What have we seen as an option? So let's see, where are we? We're here. Okay, now this one is less ambiguous. I have marked A, C, and D as visited. So those are no longer options. They're already locked in. I have B, E, F, and G as options. Which one am I going to pick? Yes, please. E, because it's the next smallest. Absolutely. And I had recorded that it's from D. There we go. So we pick that. And then I start to process the outgoing edges of E, and that's where I found an even shorter distance to B. And so you can see, originally, I thought the shortest I knew of to get to B was because I had processed A's outgoing edges, D's outgoing edges, but I hadn't gotten to B yet. So I only knew of a distance to B of 6 going along this edge and this edge. But now I know how to get to B going along this edge, and this edge. So I'm discovering new edges, and that might let me update those paths distance as I go along. That's why it was sort of like seen but not visited, because I might find a shorter route. Only when I put Y, I've locked it in, that's guaranteed to be the shortest route. Questions? Okay. You have been, oh yes, please.
Yeah, so since we are considering ADE to be as the shortest path, we would update the B row to be distance to 3 and then B to E?
Yes. So see, previously we thought the best way we knew of so far to get to B was traveling via D, and that had a weight of 6. But once we process E, we expose ourselves to a new edge, and now we can go in and update those two columns. We've seen another option. So we just replace them. Yes, please. Can I explain the process by which you know it's the shortest once you visited it? Yes. So this works in what we're going to refer to as a greedy algorithm. It means that at every step of the algorithm, we're making the most optimal choice for whatever variable we're trying to optimize for. So right now, we're trying to optimize for the shortest distance. So at every single step forward, I am locking in paths that represent the next smallest possible distance to travel. So by the time we lock something in, we guarantee that the summation of steps I've made by the time I lock it in is the shortest in sequence possible to travel. I'm going to get to an algorithm a little later today, which also kind of helps understand this. It's almost like we're optimizing for finding all of the shortest weights on the edges first and kind of locking it in by prioritizing those. We are sort of respecting like, oh, where do the outgoing edges possibly take us? But because at every single time we decide, yes, this is part of the shortest path, we guarantee that that's the next possible smallest weight we could include in the overall shortest path tree. So as the shortest path tree, that's like the list of edges that connect everything in the shortest way. From A outwards, there's a distinction. We'll get to that as well today. We're guaranteed that each of those edges, as we add them, is the shortest possible we could have added for each of those steps. Other questions on Dijkstra's? So when I ask all of you, okay, we've got some choices, which one are we going to pick? You all are all using your very complicated and sophisticated human brains to look at what's available to us and pick whichever one has the smallest known distance. Does anyone remember the structure that's going to do that for us when you actually write this in code for P4? It was like at the bottom of a slide. If you remember it, I'm going to be very impressed. I was like, ooh, we've kind of been building this thing. There's some method to the madness. Wouldn't it be nice if we had this really efficient data structure that percolates the smallest possible thing up to the top, so we always know where the smallest possible thing exists? Yeah, sure. I love it. It's a team effort. Heap, yes. Was that what you were going to say too? Yes, thank you. You're absolutely right. It's a heap. So this thing that we're doing here where we're making this decision, what's the next possible smallest place to go? Heap. That's what you're going to use in order to store each of your options. And you'll remove min in order to accomplish that. This will all make so much sense, hopefully, when you're actually looking at the code. And then you can click through these, and then we get a final result here. And remember, what we were looking at here is we are looking at the shortest distance from the start, which is vertex A, to every other vertex. So this is like the Google Maps situation. What's the shortest way to get from my house out to wherever the heck I'm going? Keep that distinction in mind. We're going to learn something new today, too. But any other questions about Dijkstra's? Yes, please. What an incredible segue. Amazing. Real quick, before I get to answer that question, just a reminder, the midterm resubmissions are on Friday. I can't take late submissions. I want to get you all your midterm scores back, and I want to release the midterm solutions so you can all look at them and do the resubs and all that kind of stuff. So please, please, please make sure that you submit your midterm resubmissions. That's the different answers for half of the points missed back, due Friday at midnight. I think that's my only announcement. Does anyone have any other administrative questions? Okay, let's talk about this negative edge weights thing. So this we did see a little bit of on Friday. So the key things to remember about Dijkstra's is, yes, once a vertex is marked as known, that means its shortest path is known. That as we build up through Dijkstra's, we use the weights to keep track and make decisions on where we're going to go, but we keep track of this thing called back pointers. That tells us from which vertex did we travel along the edge to get there. So if I ask you for the shortest path, you're going to run Dijkstra's, you're going to fill up these maps, but then you have to iterate through the map to actually reconstruct the path. So like in our example here, if I'm like, what's the shortest path to get to F? You would come in and you'd be like, F, its edge to is C, C's edge to is A, that's my source. So the shortest path to F is ACF, but I had to kind of reverse engineer it using the maps. That tends to trip students up when they're actually coding it. That's what the back pointers means. This is the order added to known set is unimportant. I just, tried to make that clearer for all of you guys. Let's see. But of course, as a reminder, if you are only looking for a specific vertex, you can stop early. You don't have to traverse the entire map if you found the vertex to which you're trying to accomplish your journey. It's a greedy algorithm. It just means I make the most optimal decision that is not about delayed gratification. This is an instant gratification type of process, and we're going to learn a couple more of them today. But to answer our friend's question, because it is a greedy algorithm, it works except for negative edge weights. Because negative edge weights, if you think about the way that would work, if you're sort of like calculating the total distance, a negative edge weight would kind of like reduce some of the distance you traveled. It doesn't make as much sense in physical graphs, but maybe it makes sense in terms of influence or something like that. And so because of the greedy nature, negative edge weights break Dijkstra's. You cannot use Dijkstra's if your graph has negative edge weights, but you can use this other algorithm. It's called Bellman-Ford, and here's a bunch of stuff about who invented it. It was one of those things where a bunch of people like simultaneously invented it, and then they argued over who got credit for it later. Here's the basics. We know if we think about a fence post, there's always, if there's V fences, there's going to be V minus 1 like separators between the posts, right? So if we have a shortest path between two vertices, we know that at longest, that shortest path will contain V minus 1 edges. It's that fence post kind of idea. So since we know that at most there's going to be V minus 1 edges, what if instead of like crawling through the graph, I looked at every vertex and examined its outgoing edges as an iteration, and we do V minus 1 iterations? This will give us the opportunity to come back and reevaluate some of the paths that we've looked at beforehand, which is what we need to do in order to be able to support negative edge weights. I am going to very quickly walk you through some of the basics of Bellman-Ford. I'm just going to be real with y'all. You don't have to implement Bellman-Ford, okay? That's why I went so much on Dijkstra's. So if this is not super clear to you, that's okay. So here we have a graph. The way that we are going to do this is we kind of do iteration 1 where we go vertex by vertex. And so we're going to start at source, and we're going to look at its outgoing edges, and we're going to say, oh, look, here's a 10 to A and 8 to E. So we're going to update. Source, of course, has a distance 0. A and E get the initial 10. And then we kind of loop through again, and we look at A, and we look at A's outgoing. And since A has a distance of 10, and it's got an outgoing of 2 to C, we can put 12 in at C. And then we go to B, and we see at that point we didn't have any way of getting to B. And so we kind of just repeat through, looking at all of the different ways that we can get to things, just iterating vertex by vertex. We're not crawling this time. We're just looping over our vertices. And we do this v minus 1 times, except if we get to a point where we are filling out our graph and we have no changes between iterations, that even gives us the opportunity to stop early. So we iterate until we have no more changes in the table, and then we can bail out. It does run slower than Dijkstra's, but you got to, because you can't be greedy in this case. You got to reevaluate the negative edge weights. You can walk through this exact example with this YouTube video, but like I said, I just wanted you to be aware that there exists something called Bellman-Ford. It's specifically for when you have negative edge weights. It does run slower than Dijkstra's. That's why Dijkstra's tends to be king in graph situations. Also, possibly a reminder that when you're designing your graph model, you can use it negative edge weights, but think about what algorithms it's going to enable you to do if you choose negative edge weights. It breaks some of the other algorithms. Yeah?
If we add like the magnitude of the minimum edge weight between each of the edges, does that make it like a non-negative graph?
Oh, like
For this one, if we add -4 to all the edges.
Ah, I see. Like it's essentially finding the smallest negative number and then scaling everything up by that so that you still get the same relative weights in relation to one another, and then you could run Dijkstra's. I could see how you could do that. I think that would work, for example, if you're just trying to find the shortest path and you're trying to treat the negatives as just in relation to the other values, but obviously the numbers you get out of it would be bunk kind of thing. So yeah, so maybe if you think about how you could scale it this way or that would work, but the actual distance numbers would be meaningless in that context. Yeah?
Do we need to understand Bellman-Ford algorithm for the final?
No, you do not need to be able to run through Bellman-Ford for the final. I might ask you, what's a great algorithm to use? And maybe Bellman-Ford is the answer, but I'm going to ask you to like click through it like I did with the Dijkstra's. I think you even have to do that on your exercise. Yeah.
What about this example with break Dijkstra?
So this one's got these negatives here. So as you can imagine, what would happen is if I was doing Dijkstra's, I would start at S, and I would go to E because that's the shortest I have available. And then I would go from E, and I would go around 1 because that's the shortest I have available. And then I would get to these negative numbers here. And I would still do my best, maybe pick -4 here. But at that point, I would lock in A. And it's possible that coming around here, doing the negative loop, I haven't done the math on it. But if I didn't catch that, I would lock something in too early. And then a negative edge weight that I might have explored later on in the Dijkstra's would actually produce a smaller overall distance. So that's why negative edge weights break Dijkstra's, is because you lock something in at the moment you think you make the best decision, but because edge weights kind of undo some of the behavior, you can't apply that same logic. Okay. Great. I'm sorry, I know I kind of rushed through that one. Like I said, Bellman-Ford's not the most important. I just want you to be aware. But something it is very important, and you are also going to have to do on P4, is something called a minimum spanning tree. So let's talk about that. That's what I really want to talk about today. Okay. This is real. This is the actual problem for which these were invented in the 1920s, and a forever reminder that computer science well predates what we think of as an electronic computer. Never forget. Okay, it is the 1920s. You and your friend at the electric company need to choose where to build wires to connect all cities to the new electrical plant. So if you remember, the way that electricity works is we have sort of one big generator, and then we line these wires, and as long as you're sort of touching one of the wires, it's like you have access to the entire grid, right? And so yes, there's some amount of friction and things like that in terms of like the distance you have to travel. But right now we're sort of thinking of this as this perfect electrical grid where the point is just as long as you're touching the grid, you have electrical service. but it's expensive to lay those wires. Maybe we have to dig under the ground. That is literally why they invented this, because they had to dig and they wanted to minimize the cost. Or maybe you have to put in telephone wires or whatever it is. You just need the smallest total sum of edge weights that still connects everything. It's not about a path. It's not about walking from one place to the other place. It's about the smallest total sum of edge weights that would bring us in connection to the electrical grid. So how do we take a look at a map like this, a graph like this, and run some algorithm to tell us what is the set of edges that would maintain total connectivity across the graph, but do so in the minimum total sum weight possible? Welcome to the minimum spanning tree problem. That's what the MST stands for, minimum spanning tree. Remember, tree is just our fancy way of sort of referring to like the subset of these vertices and edges. So if, this picture was all of the edge weights, here is the minimum spanning tree where I've removed all of the edges we don't need, and I have left the minimum set of edges that still maintain total connectivity. Now, like I said, it's not about travel. This is actually one of, I know that whole big O feels like it's supposed to be worst case thing is probably the biggest hurdle to get over in this class conceptually. For some reason, this is the other most common confusion, that minimum spanning tree and shortest path tree are the same thing. They're not. They're different. Because here's our, electrical plant. If I was actually trying to walk a path to E, there's probably much shorter ways to do it than this, because I would have to walk down this, and then this, and then this, and then this. But I don't care about path weights. I just care about the minimum total that maintains total connectivity. Now, just like that fence post thing we were talking about in Bellman Ford, we know that to connect every vertex, we're going to have V minus 1 edges. If there's V posts, there's V minus 1 chain links between them. So the minimum spanning tree will always have, at most, V minus 1 edges. If it had V edges, there would be a cycle somewhere, and then that's a redundancy, and that's some electrical wire we didn't need to have to pay to lay down. Is a MST for a given graph always going to be perfectly unique? I will tell you, if it has unique edge weights, yes. If every edge weight is different, if unique edge weights are unique, then yeah, there will be only one possible minimum spanning tree. But you will find a lot of situations where there's duplicate edge weights. And in a duplicate edge weight situation, maybe there are multiple minimum spanning trees that all have the same total summation of weights. That's what we're minimizing. So if the edge weights are unique, then there's only one answer. I.e., if I ever ask you this on an exam, I will use unique edge weights so that it doesn't get confusing. Let's see. This is just continuing to define minimum spanning trees. This is mostly what I've just said there. Okay. This is, again, the distinction between shortest path and minimum spanning tree. This is maybe what a shortest path or a Dijkstra's from the electrical factory might look like. See how it's like, oh, well, if I want to get to every edge as quickly as possible, maybe that's the way that I get there. But that doesn't necessarily mean that the sum of each of these is going to be the lowest. So you can see how these are a total sum that's smaller. There's a difference between minimum spanning tree and shortest path tree. Just about grid connectivity. Great. Okay. So that's the minimum spanning tree problem. Let's talk about how to actually solve it. So there are kind of two generally popular algorithms in order to accomplish this. You can think of this, in terms of thinking either vertex by vertex or edge by edge. So these both work. One is named Prim's algorithm. One is named Kruskal's algorithm after people, again. For P4, you are going to be asked to implement Kruskal's algorithm. But surprise, you need another data structure to do that. We're going to meet that on Wednesday. So the way that we think about it is instead of starting from one particular source, because we don't care. It's not about a source to a target. We're going to kind of sort the different edge weights within the graph and pick those as we go by. So this is just a visualization of how the graph is explored running either Dijkstra's or Prim's. And Prim's, as you can see, kind of jumps around because it's not crawling through the graph. It's just sorting the edge weights and then picking as we go. So let's see. I want a better one. Here we go. Let's walk through the actual algorithm of how Prim's works. So, wait, hang on. I don't like these either. These are mostly so that you can read them on your own. Yeah. Okay, fine. Let's do Kruskal's. I think Kruskal's is easier. Frankly, you're not really responsible for Prim's in this class. Okay, so the way that I like to think about this MST thing, again, you've heard me refer to this as like the islands. I like to think of vertices as islands, and then the edges as ways maybe to hop between them. Maybe they're bridges. I don't know, however you think of it. And so the way that Kruskal's algorithm works is we think of each vertex initially starting as its own independent island. They're all separated from the electrical grid. And what I'm going to do is I'm going to look at the list of edges and I'm going to sort them. And I'm going to start with the smallest possible edge, the smallest edge that exists anywhere in the graph. And I'm going to look and see, does it connect two previously unconnected vertices? Does it connect together two previously disconnected islands? And if the answer is yes, I now officially mark it as in my MST, and then I go to the next smallest edge. I'm just looping over the edge weights in sorted order, and I'm asking myself, does including this edge bring a new island into the archipelago as we move through it? So, great, thank you. The smallest edge here, I know I've sort of grayed them out, but if you look at all of these numbers, the smallest edge anywhere on this entire graph is this value of 1. That 1 connects A and C that we sort of, had initialized to being independent. So that extended the connectivity so we bring it into the fold. Now I look here and I see the next smallest edge weight is 2. 2 will connect B and F, previously disconnected groupings. So I will include it. I look through this graph and I see this value 3 is the next smallest edge weight. And I ask myself, does it extend connectivity to include it? And it does, because D was not previously connected to A and C. I look at 4. 4 would connect this group of A, C, and D with this group of B and F. So I am going to include it. Now I have consumed 1, 2, 3, 4, 5 of my islands are now connected, but we've got this lone little E over here that's disconnected still. But I'm still going in edge sorted order. So I look here, the next largest edge is this 5 between C and D. Should I include that 5 or do I need it? Is that 5 unnecessary? I see a lot of head shaking. Yes, the 5 is redundant. It would cause a cycle because C and D are already connected to each other, though sort of, indirectly. But that's okay. It's not about the distance between C and D. So I'm going to skip that 5. And then I'm going to look over here, and I see 6 is the next smallest one, and 6 will connect that E, and then I'm done as soon as all of the vertices are connected. So all you do is take every edge weight, you sort it, and then you just go in order of the sorted edge weights and ask yourself, does this extend connectivity? And now I've built the minimum spanning tree of this graph. Questions on that algorithm? Yes?
Is it possible for this algorithm to connect a second vertices that's smaller than the previous vertices? Let's say for connecting the islands to C.
Uh-huh.
The first one was 5, and I guess my only question is, would this algorithm prevent any previously decided vertices from being like incompatible?
I'm not entirely sure if I understand, but I will tell you, so if you can't tell, this is another greedy algorithm because I sorted by edge weight, and so I'm always starting at the smallest possible edge that could be included, and whether or not it checks my box of, yes, it extends connectivity. So I'm guaranteed that I'm never going to accidentally add a cycle because I've got some protections in there, and I'm guaranteed that I'm not going to accidentally later on find a better way to connect items. When you say two edges that are smaller, I'm not sure what you mean by that piece of it.
You just answered my question
Okay.
before. Yeah, so I think the way you're describing the algorithm in that it never chooses an edge that is smaller than a previous one to connect to a node.
Yeah. Since you always go in order of the sorted edges, you're guaranteed that the one that extends connectivity is the smallest possible one you could use. So by the time you get to any other ones that might cause a cycle, you can check like, oh no, those islands are already connected. So ignore that larger edge. So the greedy nature of this guarantees that it will work. Yeah. What if there are two edges of the same weight? Then you can just do your sort of tiebreaker thing, probably based on the data stored in the vertex. But you always ask yourself, does it extend connectivity? But in that case, like I said, maybe there's two different possible orientations of the MST that are valid, and that might be totally reasonable. Yeah? Good question. Since this is similar to Dijkstra's and that greedy, I'm just like making the best decision as I go. When everything's officially connected, you're done. You don't have to keep going. So as soon as all of the islands are connected, break out. It's not worth your time checking the other ones. Yeah. Great question. Because I keep being like, extending connectivity, right? And your question is, well, how do I know when everything's connected? Actually, as of right now, this would be really hard to do. Like maybe if you did it in a set and you were constantly checking if like these things were in this set or that set or something like that, wouldn't it be nice if we had a data structure that maintained multiple sets and let you union those sets together? That's something called a disjoint set, and that's our new data structure that we will be learning on Wednesday, and that's how you'll know whether or not everything is connected, because essentially we're going to maintain each of the islands as independent sets, and when you add a vertex in between them, you mark them as unioned, and so you go until there's only one set left, essentially. Yeah? Oh, like when I'm considering, which one? That 4? That step? So you're right. To clarify, the connectivity is between these sort of ever-growing islands. I don't know. Is there some like microbiology analogy for this where like cells consume each other or something? I need a better analogy than islands, somebody. But right now, what we would essentially do is we would see that the edge 4 connects vertices A and B. And we would see that A, let's say A is in group 1. And we would ask, is B also in group 1? It's not. So it's really just about, are these two vertices in different groups from one another? So since B is not in the same group as A, then we know adding that 4 extends the connectivity. It merges those two groups together. So that's why when we get around to the 5 between C and D, we ask ourselves, are C and D in the same group? Yeah, they are. So we don't need to continue to extend that connectivity. So we skip that edge 5. Because C and D are already connected right now. They're already in the same island chain. I don't know, they're connected by bridges, whatever analogy works for your brain. So we don't need to add that. And essentially what we'll do is in the disjoint set, we'll check, are these two things connected? Are they in the same set already? And if the answer is yes, you skip that edge. Other questions? Cool. Okay, let's see. There we go. Great. Let's talk about the code real quick, and then I'll give you a chance to try it yourself. So if you can see, it is kind of looking similar to our graph code. You know, we've got a set that maintains the edges. That's our final result. We've got that. And then, you know, we sort of initialize every vertex as a unreachable island. So we have that sort of V runtime that's like, hey, separate all the islands. It's sort of like you saw I grayed out the edges. It's like we kind of ignore all the edges for a second. Then we sort all the edges by weight, smallest to largest. And then we loop over each edge in sorted order. And we find what group is the thing on one end of the edge and what group is the thing on the other end of the edge. So here, you can think of U and V as the names of the vertices on either ends of an edge. So in that conversation where we were talking about what happens with 4, if we're considering edge 4, let's say A is UMST and B is VMST, and if those are not the same group, then we're like, sweet, this extends connectivity, we add the edge to our final MST, and then we union those two groups together. So now, if I were to call the same thing again, it would be like, oh, A and B are in the same group. You don't need to keep adding. Yeah?
What is the dot find method return?
The dot find method, and again, this we will talk about on Wednesday, it's going to return a representative of that group. So when I was like, okay, let's say A is in group 1 and B is in group 2, I just gave it some names so we could tell the difference between those two groups. That's what it's actually returning, a little representative, so we can tell if they're in the same group or not. And we'll get into the delightful nitty-gritties of how you pick the representative and all that good stuff on Wednesday. Okay, why don't you all give it a try? So here's the pseudocode. Here are all the edges. I represented them as like the parentheses, thing on one side of it, comma, thing on the other side of the edge. Sort the edges by weight, go in order, add them in order. That extends connectivity. Go ahead and take 3 minutes and discuss. We'll come check back in. All right, let's chat about it. So first things first, I'm going to sort my edges, and then I'm going to work in edge sorted order. So what is the smallest edge anywhere on this graph? Yeah, sure. 1 between A and C. And so we are going to initialize every vertex as being its own island. So if you can't tell, the answer to including the first edge is always going to be yes, because at this point A and C are not in the same edge weights, right? So should I do this iteratively? Yes. So we are going to include A and C because they were previously in 2 separate islands. So now, if we previously had 1, 2, 3, 4, 5, 6 islands, now we only have 5 islands, where one of them is a little bit bigger, right? That amoeba has like consumed A or something like that. Okay, now, what is the next smallest edge? Yeah, C to E. And would you select C to E to be part? I agree, yes, because E was a little island unto itself, connected to nobody. But C came along, C is going to be its friend, so we're going to include it. Okay, if you can't tell, I put the edges in sorted order here now. So A and B is the next smallest. What do we think? Do we include it? Do we not include it? Yeah, I see a lot of thumbs up. If you can't tell, we kind of get this pattern where the smallest edges, it's mostly a yes in the beginning, right? Things are mostly disconnected. So this is how we kind of make sure we do have the smallest MST. We are very highly indexed on keeping the smallest possible edges. So, yep, we're going to include A to B. What about A to D? Yes, we keep it. No, we don't. Okay. Yeah, I see some thumbs ups. Absolutely. You're correct. Yes, A to D, because D was just hanging out by itself. So right now, how many islands do we have total left in the graph? How many groupings of connectivity? Yes, correct. There's 2. There's A, B, C, D, and E are all now connected, but poor little F is waiting in the wings, waiting to be connected some way, somehow. Question? Sorry, question there? Or are you just stretching? Never mind. So we're going to keep going. C to D. Yes, we include it. No, we don't. I agree. C and D are already connected. They're already part of, we'll call it, group 1 or whatever, the big group there. So we are not going to, because it would cause a cycle. Okay, what about B to F? Yes, we include it. No, we don't include it. Yes, exactly. Because we finally have found a way to get to F. And so to our friend's question earlier, do we even really need to keep looking at things? Or can we bail out early? You can bail out early. Another common pattern with greedy algorithms. We're going to get this answer. We're going to get it as fast as possible. And then when we found our answer, we don't need to worry anymore. So the rest of these are just no, no, no. So this is a very common pattern in prims. You say yes a lot in the beginning, maybe a no here and there in cycles until you finally connect everything, and then it's all no's. Questions on how that algorithm works? Yes?
So one conclusion is that once the algorithm has seen every letter in like the second slot of the edge, then the algorithm is concluded. You don't have to search anymore.
Yes. And I totally understand why you said second slot of the edge, because that's how it looks like here. So come back on Wednesday to meet the disjoint set, which will actually store these little islands in a way where we'll know what's connected and what's not connected. Guess what? You will be implementing your own disjoint set. Yay. Okay. Thanks so much, everyone. Yeah. We'll start here. Hey.